Okay, so we're starting into Chapter 7. It's on page 522. 7.1, equivalent rational expressions. So we're looking at rational expressions and equations. An expression means that we really have just one side of the equation, no equal sign in between. Rational, fancy word for fraction. So we're going to be dealing with fractions here. And these fractions are going to have the variable in the denominator. Okay, so looking for now which values of x will this allow it to be defined and not defined. We're looking for restrictions. We know that you're not able to divide by 0. So we're looking at the denominator here. We can't divide by 0, so what values are going to make x equal to 0? We say, well, x cannot be equal to 0, but it can be anything else. So we'll say x ER from there. Second one, there's no restrictions because there is no denominator here. So in this one, x can be anything. Third one, 3 plus x. Again, there's no denominator, so we don't have any restrictions. X ER. Now, 5 divided by x, same thing as saying 5 over x. We now have a denominator. That denominator cannot be equal to 0, but it can be anything else. So we throw the XER on the end. Evaluating these. If we plug in a 2, we're going to get 6 over 2. That's going to be equal to 3. No problems there. If I put in 0 now for that x, we've got 6 over 0. Problem, that's undefined. Can't divide by 0. If I plug in a 1, I've got 6 over 1. That equals 6. No problems there. 4x over x plus 2. Plug in the 2. We get 4 times 2 over 2 plus 2. And that's going to give us 8 over 4, which is equal to 2. But if I plug in a 0 now, that was a problem in the first one. Is it going to be a problem here now? 4 times 0 over 0 plus 2, which is going to give us 0 over 2. That's not a problem. It's dividing by 0 when the 0 is in the denominator, not 0 in the numerator. That's fine. It's just equal to 0. Next one, if we have 4 times 1 over 1 plus 2, we have 4 over 3, and that's not a problem. Let's look at the next one. 3 over x minus 2. So let's plug it in. 2 minus 2. 2 minus 2 is 0. That's a problem. That's undefined. If I plug in a 0, 3 over 0 minus 2, we just get negative 3 over 2. Because it's 0 minus 2, which was negative 2. Again, it's okay to put 0 into this one. The problem came when we put 2 into that one. If I plug in a 1, I get 3 over 1 minus 2, which gives us 3 over negative 1, so negative 3. No problem there. Oh, this next one. Now we've got a quadratic that we're going to be plugging into. So 2 over 2 squared minus 6 times 2 plus 8. When we plug this in and work it through, we've got 4 minus 12 plus 8. That's equal to 0. We're undefined on this one. So we can't be using 2. Plugging in 0, 0 is going to be fine. We're going to have 0 over 0 squared minus 6 times 0 plus 8. That's 0 over 8, which is just 0. And if we plug in a 1, 1 over 1 squared minus 6 times 1 plus 8, which is going to give us 1 over 3 when we work it out. Looking at this next one, we have it in factored form. Plugging in a 2, we're going to have 3 over 2 minus 1 times 2 plus 2. Notice that neither of those two factors go to 0, so it's not going to be a problem. We're going to get 3 over 4. If I plug in 0 for the x, 3 over 0 minus 1, 0 plus 2, I've got 3 over negative 1 times 2, negative 3 over 2. Neither of those two factors went to 0, so we're not going to have the denominator going to 0. If, however, I plug in a 1 minus 1, and 1 plus 2, that first fraction is going to go to a 0. Because one of these goes to 0, the whole denominator is going to go to 0. We're going to have 3 over 0 times 3, which is 3 over 0. There's the problem. This is undefined. So this is where the factoring is going to come in. When we have a quadratic in the denominator, we're going to have to factor to be able to move further with that. Okay, so when the numerator and denominator fraction are integers, the fraction is a rational number. When the numerator and denominator of a fraction are polynomials, the fraction is a rational expression. This is what it's talking about here now. A rational expression, fancy way of saying a fraction. That's all that's saying. Quotient of two polynomials, just meaning fraction. Examples there that they give. Okay. X's and Y's, numerator and denominator. A rational expression cannot contain roots of variables, or variables that have that are the exponents. So we cannot have 2 to the x or square root of x. It's always just going to be x squared, x cubed, or just x to the 1. Rational expressions are not defined for values that make the denominator 0. We cannot divide by 0. We call those non-permissible values, NPVs. I will call them NPVs all the way through. I'm not going to say non-permissible values. They're the restrictions. They're what make the denominator equal to 0. So the expression x plus 5 over x minus 3, we look at what value is going to make the denominator equal to 0. Well, if x equals 3, we're going to get 3 minus 3 in the denominator. So x equals 3 is an NPV. Or we can say that x cannot equal 3 for the restriction. But the NPV is 3. So now we want to know what values will make the denominator equal to 0. That's what the NPV is talking about. We look at the denominator, pull that out. X squared minus 9. Well, that cannot equal to 0. Well, we've got two methods to be able to do this. One is to factor it, and two, right now, we could just solve for the x. I'm going to show both methods. Add the 9 to the other side. We've now got x squared cannot equal 9. Square root both sides. When you take the square root, plus or minus in front. So then we get x cannot equal plus or minus 3. If I put a positive 3 or a negative 3 in for x, the denominator will be 0. The other way I could do it is say, hey, this is a difference of squares. Let's factor that. X squared minus 9 cannot equal 0. Squaring that, or sorry, factoring that, we get x plus 3, x minus 3 cannot equal 0. Treat it exactly the same as you would if it was equal to 0. Okay, so then x plus 3 cannot equal 0, or x minus 3 cannot equal 0. So x cannot equal negative 3, or x cannot equal positive 3. Those are the restrictions. Same as what I had right up here, plus and minus 3. You will see sometimes they'll say, when they're actually asking for the non-permissible values, they'll just use the equal sign, and they'll say, well, the NPV is when x is equal to plus and minus 3. I'm going to show you just to say it cannot equal because that's the restriction on it. That's what the domain is restricted to. Next one. Find the denominator, pull it out, and say that it cannot equal 0. This is identical to the quadratic solving that we did in Chapter 3. The only difference is we're changing it from a equal sign into a not equal sign, but we treat the algebra identically. We're just going to factor this. Sum is equal to negative 8. Product is equal to 16. Two numbers that we have, plus and minus 4. Sorry. Thanks. So for this one, so it's going to be a minus 4 and a minus 4 that we have. So we've got x minus 4 times x minus 4 cannot equal 0. Pull each of them out. Hey, they're both the same. So I only have to do it once. So x cannot equal positive 4. There's my NPV. Is this expression defined for all values of x? Give you a chance just to think that one through. And so now we look at it and say, well, that denominator, can I make the denominator equal to 0? Is there something I can do to make that equal to 0? Pull it out. 2x cubed plus 2 cannot equal 0. Start solving for x. 2x cubed cannot equal negative 2. X cubed cannot equal negative 2 over 2. X cubed cannot equal negative 1. Cube root both sides. So x cannot equal negative 1. If I had a square root though there, I'll just take it a little bit further. If it was at this point, well, what if it was x squared cannot equal negative 1? I would take the square root of both sides, and I would get x cannot equal the square root of negative 1. Well, yeah, the square root of negative 1 is not a real answer, so then we would say no NPVs. There's no restriction if this is the case. Because we can't get x equal to the square root of negative 1, so therefore there would be no restriction, or the domain in that one would be XER. I could have anything for x at that point. Okay, so to write equivalent form of a rational number, multiply or divide the numerator and denominator by the same number. For example, 12 over 8, hey, I can change that and get to 36 by multiplying by 2. As long as you're multiplying by a form of 1, or dividing by the same thing. You can either multiply or divide by the same. And those three are all equivalent fractions. Same thing we can do when we are dealing with variables. And this is all that's saying. I can go ahead and multiply by x. I can divide both of them by 2x. As long as I'm doing the same thing to numerator and denominator, multiplying or dividing, I still have it equivalent. So those three are all equivalent. Okay, so I'm going to get an equivalent form here. We want two different equivalent forms. That means I could multiply by something, I could divide by something. X plus 5 times x minus 1 over 2x minus 1. You could multiply by whatever you want and it'll still be equivalent as long as you do the same to numerator and denominator. I'm going to look and say, hey, why don't we multiply both of them by x plus 5 over x plus 5. That would just give us x plus 5 squared times x minus 1 over 2 times x minus 1. That one's not really the important part. This next one here is the very important part that we're trying to get at for this chapter. So we're going to start this part. X plus 5 times x minus 1 over 2 is x minus 1. I'm going to divide both the numerator and the denominator by the same thing. And I notice here that they both have a common factor. I want to make sure I'm dividing by a factor in brackets this whole package, not just part of it. I can't just divide by an x. I want to divide by a whole package. And in that case, if I divide it by the numerator by x minus 1 and the denominator by x minus 1, those are going to cancel off to 0, or sorry, cancel off to 1. Which is going to leave us with x plus 5 over 2. And that's the important part, is where we're canceling off or dividing a common factor to 1. So using that concept, we're going to write each rational expression in simplest form. We're going to look for what's common in the numerator and denominator that we'll be able to divide to 1. We're going to take each part as its own fraction. So the numbers, the coefficients in front, the a's, the b's, and then the c's. We've got negative 25 over 35. Well, I can take out of both of them, I can take 5. So I'm going to divide the numerator by 5, which is going to give me negative 20. I'm going to divide the denominator by 5. Oh yeah, we got a 7. Oops. Should have been a 20. That should have been a 5. Right. And a 5 over 7. So we divide both of them. Then we look at a. I've got an a cubed on the top, I've got an a on the bottom. I can divide those ones off to take out an a. That's going to leave me with a squared in the numerator. So right now I have negative 5 over 7, a squared in the numerator. Then I've got the b's. B squared numerator, b to the 5 denominator. We can use our exponent laws, if you want to think of it that way. B to the 5 minus 2. I'm going to go to whichever one has the bigger exponent, so that it's always positive. There's 2 in the numerator, there's 5 in the denominator. So I'm going to cancel off 2 of them here, cancel off 2 of them there. It's going to leave me with b cubed in the denominator. C has nobody to play with, so he's just going to stay as such. And that's the simplified answer. Let's do another one there. 6x squared plus 12x over 3x. Two different ways. I can either give all of them the love, or I can factor. I'm going to show you the factoring method because we're going to be factoring most of them. So let's factor the numerator. I can take a GCF out. That's going to leave me with, I can take out 6x. 6x, and I get left with x plus 2 over 3x. And now I can start dealing with those two together. 6x and the 3x. 6x can divide by 3x, give me 2. 3x divided by 3x will give me 1. So I'm going to get left with 2 bracket x plus 2. Now, one thing we have to also be looking at is saying, I canceled stuff off, and I'm saying that it's equal. In this second one here, this 2x plus 2, I don't have a denominator. So it's showing me that there's no restrictions. But I've said that it's equal all the way along. This is equal to the original. I have to talk about the restrictions right from the very beginning.
Could you contact the office, please?
So I've got a 3x here. I have to say what is going to make that equal to 0. And in this case, comma, x cannot equal to 0. That's my full answer. Same thing with part 1. I've got an a and a b in the denominator. Those can't be 0. So comma, a cannot be 0, and b cannot be 0. Or you can say a comma b cannot equal 0. That's the full answer. Let's look at part C. Factoring the numerator, factoring the denominator. And then we can continue with it. So we're going to say that it is equal to difference of squares here, so x plus 7, x minus 7, over factoring that denominator. Sum of -5, product equals -14. And that gives me -7 and a positive 2. So x plus 2, x minus 7. This is the point at which I want to do my NPVs. So right now I'm going to say I can't have x plus 2 equaling 0, and I can't have x minus 7 equaling 0. So x cannot equal -2 from the first one, because that will make it 0. I can't make this one equal to 0 either, so 7. I'm going to put those down right now, because that's the step I have to do the NPVs from. And now I look at, are there any packages inside the brackets that I can divide out from both numerator and denominator? And I can. The x minus 7 is in both. It's got to be exactly the same, and they have to be in brackets. It has to be a whole package. A whole package for nothing auto. We hiya those two, which leaves us with x plus 7 over x plus 2, where x cannot equal -2 or 7. And the last one there. Got to factor the numerator, got to factor the denominator. So factoring the numerator here. We've got sum equal to -5. We've got a product equal to 2 times -3, which is equal to -6. So my two factors are going to be -3 -6 and 1 there. So do our factoring part. That gives us x minus 6, x plus 1. Divide each of them by the leading coefficient. Gives us x minus 3 and 2x plus 1. Let's bring that back into the question now. The numerator is going to be x minus 3 times 2x plus 1 over denominator 9 minus x squared, difference of squares. That one's going to factor into 3 plus x, 3 minus x. And I look and say, oh, nothing's exactly the same. But if I would do one thing here, if I would factor out a -1 out of either the numerator or the denominator here, I can make these the same. So I'm going to factor out a -1 out of that x minus 3. Pull a -1 out of there. That's going to give me -x plus 3 times 2x plus 1 over 3 plus x, 3 minus x. Well, -x plus 3, let's rewrite that. Let's change the order. Let's say 3 minus x in that order. So we now have -1 times 3 minus x times 2x plus 1 over 3 plus x, 3 minus x. We now have two of them that are exactly the same. I can cancel those ones off, which will give me -1 bracket 2x plus 1 over 3 plus x. We can leave it as that. If you would rather write x plus 3, you can do that in the denominator as well. We've got to do our NPVs. We do our NPVs before we start canceling off any. So here's the step where we start canceling off. We've got to go a step above and do our NPVs from there. So in this case, x cannot equal plus or minus 3. So comma, x cannot equal plus or minus 3. There's the full answer.